Welcome back to the Deep Dive. Today, we are shifting gears a little bit. We're usually looking at a specific book or maybe a historical event, but today we're looking at something that is, well, it's likely staring you in the face right now. We're looking at the invisible nervous system of the modern enterprise. We are talking about the grand architecture of audiovisual systems.
It is absolutely one of those topics that feels, almost mundane until you stop and realize the sheer engineering density required just to make it all work seamlessly.
Exactly. I think for most of us, AV is just plugging in a cable, but we have a stack of technical documents, system diagrams, and white papers here that paint a very, very different picture.
They certainly do.
So our mission today is to explore how enterprise AV functions as a single integrated ecosystem.
And this isn't just for the tech obsessed. I mean, if you're a CXO, an IT head, or, just someone who wonders why the video conference worked perfectly in one room and failed miserably in another, this breakdown is absolutely for you.
We are going to deconstruct this grand architecture step by step. We have a lot of ground to cover, from, I guess, the physics of a microphone all the way to the logic of a network switch. But before we get into the weeds, let's define the problem. Why do we even need an architecture? Why can't we just buy a nice TV and a good webcam?
Because that is what we call the Frankenstein approach. And in the industry, you see this all the time. A company goes out and buys expensive gear, a great camera from brand A beautiful screen from brand B, top-of-the-line audio from brand C, and they just stack them in a room.
And hope for the best.
And hope for the best. But that isn't a system. It's a pile of electronics.
It's a monster made of mismatched parts.
Exactly. And monsters tend to behave unpredictably. This is where the role of the system integrator, the architect, becomes so crucial. Their job is to take those disparate boxes and really to force them to speak a common language.
A true AV system, then, it's more like a biological organism.
That's the perfect analogy. It has eyes, it has ears, a brain, a voice, and a nervous system connecting everything. Without that nervous system, the parts can't coordinate.
I like that biological model. It gives us a map to follow.
Yeah.
So our roadmap for this deep dive is going to be the signal flow itself. We're going to follow the data from start to finish. And the most fundamental law of AV, the thing that governs everything, is that three-step block diagram. Inputs, processing, and outputs.
It sounds incredibly simple, but absolutely everything we're going to discuss fits into one of those three buckets.
Yeah.
Information comes in, the brain manipulates it in some way, and the result is sent out for humans to experience.
Okay, then let's start at the source. Section 1, the input layer, the eyes and ears of the system. And let's begin with the visual inputs. In, I would say, almost every modern meeting room or classroom, the centerpiece is the interactive flat panel display, or IFPD.
Right, and we need to be really careful with the terminology here. This is not a TV. A television is a passive device, you just watch it. An IFPD is an active input device, you interact with it.
It's basically a giant tablet.
That's the best way to think of it. It's a giant professional-grade tablet, and it's usually running some version of an Android OS as its backbone.
But the real differentiator, the thing that makes or breaks it, seems to be the touch experience. I've used some where the ink, it lags behind your finger, or it feels like there's this weird gap between the glass and the image.
And that all comes down to the sensing technology being used. Older panels or, cheaper consumer-grade ones use infrared or IR.
How does that work?
It creates a grid of invisible light beams right across the surface of the screen. When your finger breaks that beam, it registers a touch at that coordinate. The problem is something called parallax, that gap you mentioned between the glass and the actual display, and it's really susceptible to interference.
So even a shirt sleeve brushing against it could trigger a touch.
A sleeve, a fly landing on the screen, even strong ambient light can sometimes cause false touches. It's just not precise enough for professional use.
So what is the enterprise standard then? What makes the good ones feel so much better?
Capacitive sensing. This is the exact same technology that's on your smartphone. It uses the natural electrical conductivity of the human body to distort a tiny electrostatic field on the glass. It's incredibly precise, down to the sub-millimeter. And, more importantly, it allows for a process called optical bonding.
Optical bonding, what's that?
That's where the manufacturer glues the cover glass directly to the LCD panel with a special optically clear resin. There is literally no air gap. So when you write with a stylus or your finger, the digital ink flows from the exact point of contact.
It feels real.
It changes the psychology of the user. If the writing feels fake or disconnected, people just won't use the whiteboard features. It has to feel natural.
Okay, now let's talk about the signal flow here, because I think this is where people get confused.
Mm.
If I plug my laptop into this board to present my slides, how does the touch information get back to my laptop so I can, say, advance the slides by touching the screen?
That's a fantastic question, and it's a common point of failure. It actually requires two completely separate signal paths. You send your video to the screen via an HDMI cable, but the screen sends the touch coordinates back to your laptop via a USB cable.
Ah, so you're plugging in two things.
You're essentially plugging in a monitor and a mouse at the exact same time. If you forget to plug in that USB cable, you'll see your presentation on the big screen, but you won't be able to control it. The touch won't work.
That makes perfect sense. Okay, let's move on to the other primary eye of the room, the camera. This piece of hardware has evolved massively in just the last few years. We aren't just talking about capturing light anymore, we're talking about capturing data.
That's why we call them data video cameras now, not just webcams. The basic pipeline is, of course, the same. Light enters the lens, it hits a CMOS sensor, and an internal processor converts that into a digital video signal. But the modern difference, the game changer, is the AI layer that sits on top of that video stream.
And this is what enables the auto-tracking feature we see everywhere now.
Correct. And there are, broadly speaking, two ways this works. The first is optical. The camera uses computer vision, a machine learning model, to recognize facial landmarks, eyes, nose, mouth. It draws what's called a bounding box around the people it sees in the room, and then mechanically moves the camera, that's the PTZ, pan, tilt, zoom, to perfectly frame them.
And the second method?
The second is audio triangulation. This is really clever. The camera has its own built-in microphones, or even better, it listens to the room's main audio system. It then calculates the time of arrival difference of the sound waves hitting those mics.
So it can tell where the sound is coming from.
Precisely. It detects that a human voice is coming from a coordinate, say, 45 degrees to the right and 12 feet away. It then spins the lens to point directly at that spot.
That sounds incredibly difficult to get right, to make it look smooth and not robotic.
It is. The real engineering challenge is in the damping and the logic. You don't want the camera to whip around every time someone coughs or drops a pen. The algorithm has to make several decisions in a split second. Is this a human speech pattern? Has the person been speaking long enough to warrant moving the camera? Is there another person already speaking?
So there's a lot of logic programmed into it to make it feel natural.
A huge amount. The best systems are the ones you don't even notice are moving.
Let's quickly touch on a more specialized camera, the document camera, or what some people call a visualizer. Is that technology dead in the age of high-res webcams?
Not at all, but it is very niche. In specific verticals, think legal, medical, or engineering training, you absolutely need to show physical objects in high definition. You might need to show a clause in a contract, a circuit board, or a tissue sample. A standard webcam simply cannot focus that closely.
And the lighting is different, right?
Completely. A visualizer uses a specific optical macro lens designed for close-up work, and it has its own dedicated shadowless LED lighting to render texture and detail perfectly. It's a niche tool, but for those who need it, it's irreplaceable.
Okay, before we leave video inputs, let's just clarify the roads these signals travel on. We hear terms like HDMI, SDI, USB, and IP thrown around all the time. Can you give us a quick hierarchy of what they are and when you'd use them?
Absolutely. Think of HDMI as your local street. It's everywhere. It carries very high bandwidth video and audio, but it degrades really quickly. You generally can't run an HDMI cable more than, say, 10 or 15 meters without needing a booster. It's for connecting things within a room.
Okay, so that's the local street. What's next?
SDI is the highway. It stands for Serial Digital Interface. It's a locking, robust cable used in the broadcast industry. You can run an SDI cable 100 meters without any signal loss. It's built for reliability over long distances.
And USB?
USB is the peripheral road. It's for connecting a device directly to a host computer. Think your webcam or the touchback from an interactive display. It's not really designed for long-distance video transport on its own.
And finally, IP. You called it the teleporter.
I did. IP, or Internet Protocol, is the teleporter. It completely changes the game. It enables what we call networked video, or AV over IP. You take the video signal, you turn it into data packets, and you send it over a standard Ethernet network.
So it can go anywhere.
Anywhere the network goes, across the building, across the campus, or even across the world, you're no longer limited by cable lengths. This is, without a doubt, the future of signal distribution.
Okay, that's a fantastic breakdown of the eyes.
Yeah.
Now let's look at the ears of the system, the audio inputs. You have a note here in our documents that says, audio is mandatory, video is glamorous.
It's the golden rule of our industry. You can survive a meeting if someone's camera freezes. It's annoying, but you can get through it. You absolutely cannot survive a meeting with broken, unintelligible audio. The entire meeting just stops.
So the input layer for audio is arguably even more critical.
It determines the quality of the entire call. It is the classic garbage in, garbage out principle. If you capture bad audio at the source, no amount of processing later can truly fix it.
The big trend right now, especially in corporate spaces, is the ceiling microphone array. You see these tiles on the ceiling that look a bit like air vents. How does a microphone on the ceiling hear me clearly when I'm sitting at a table 10 feet away?
This is where we get into some really amazing physics. The technology is called beamforming.
Walk us through it. This sounds complex.
It is, but the concept is understandable. A standard single microphone is omnidirectional. It hears everything in the room equally. The hum from the AC unit, the traffic outside, the sound of someone typing on a laptop.
All that noise gets mixed in with the voice.
Exactly. A beamforming microphone array, on the other hand, contains dozens, sometimes over 100, tiny individual microphone elements inside that single housing. When you speak, that sound wave from your mouth hits each of those tiny elements at a slightly different time.
Because there are different physical locations.
Just millimeters apart, but it's enough. The digital signal processor, the DSP, inside the mic measures those tiny time differences. By applying a very precise delay to the signal from each element and then combining them, it can mathematically steer a zone of sensitivity. It creates a virtual invisible beam that focuses directly on your mouth.
So it's like using software to build a virtual shotgun microphone.
That's a perfect way to put it. It uses constructive interference to amplify the sound coming from the direction of that beam. And it uses destructive interference to cancel out the noise coming from all the other directions, what we call the null directions.
And I've seen these systems where the beams can actually track you as you move around the room.
Yes, that's the location tracking part. The processor is constantly scanning the room for sound sources. If you stand up and walk over to the whiteboard while you're talking, the beam will disengage from your chair and re-engage on your new position at the whiteboard. It's like having a sound operator with a boom mic following you, but it's all done with math.
That explains the significant cost difference between a high-end ceiling array and just using the mic on a webcam. It's a completely different class of technology.
Completely. One is a passive listener, the other is an active hunter.
What about when you need more mobility? Let's talk about wireless systems, the handheld mics or the lapel mics a presenter might wear.
Wireless is fantastic for freedom of movement, but it's tricky because the airwaves are incredibly crowded. You have Wi-Fi, cell phones, even microwave ovens, all competing for radio spectrum.
So interference is a big risk.
It is. The major shift we've seen is from older analog RF systems to modern digital systems. Digital wireless allows for two critical things. First, it's more resilient to interference, but second, and this is crucial for corporate and government work, it allows for strong encryption.
So no one can listen in.
Exactly. In a sensitive corporate boardroom meeting, you cannot have your strategic audio being picked up by a simple radio scanner in the parking lot. Digital transmission with AES 256 encryption prevents that entirely.
I often see wireless receivers with two antennas sticking up. Why two? What's the point of that?
That's a technology called diversity, or more specifically, antenna diversity. It's designed to combat a problem called multipath interference. Radio waves bounce off walls, windows, and people. Sometimes the direct wave from the microphone and a bounced wave hit the receiver's antenna at the exact same time but out of phase, and they cancel each other out.
A dropout. The audio cuts out for a split second.
That's the one. Diversity receivers have two antennas spaced a few inches apart. The logic is simple but brilliant. It's statistically almost impossible for a multipath dropout to occur at both antennas at the exact same instant. The system is constantly monitoring the signal strength from both, and it switches to the strongest one thousands of times a second.
So you never hear the switch. It's seamless.
Completely seamless. It's a fundamental feature for any professional wireless system.
Okay, one last microphone type to cover. The gooseneck. The classic conference table microphone.
Still the absolute best for raw audio quality, for one simple reason: proximity. Physics always wins. The closer the microphone is to the source, the person's mouth, the better the signal-to-noise ratio will be.
But the problem comes when you have a lot of them, right? If you have a boardroom with 50 seats and 50 live mics.
You have a disaster. If all 50 of those mics are on or open at the same time, you get this horrible, hollow, cavernous room sound. Picks up every shuffle, every cough. This is where we solve the problem with auto-mixing logic.
Is that just like a noise gate that turns the mic off when no one is talking?
It's similar, but much smarter. A simple gate can sound choppy. Modern auto-mixers use a principle called gain sharing. Imagine the total available audio volume for the room is a pie. If one person speaks, their microphone gets the whole pie. If two people start speaking at once, the system automatically and imperceptibly lowers the level of both of their mics slightly, so they perfectly share the pie.
So the total energy in the room stays constant.
Precisely. This prevents feedback loops and keeps the background noise floor incredibly low because only the microphones that are actively being spoken into are given significant gain.
Okay, we've covered the eyes and the ears. They're capturing all this information. But how does the user actually control the system? This brings us to the final part of the input layer, the commands or control inputs.
This is the human-machine interface. Most commonly, it's the touch panel sitting on the conference room table.
And it's important to understand, this isn't just an app running on a standard iPad, is it?
It really isn't, and that's a key distinction.
Yeah.
While some systems use iPads, a dedicated professional touch panel is a hardened device. But more importantly, it's a control surface that is sending specific commands over the network. When you press a button that says presentation mode, it's not just switching an input on the screen.
It's triggering a macro.
It's triggering a cascade of commands. It's sending a TCP/IP command to the lighting controller to dim the lights to 30%. It's sending a different command, maybe an API call, to the blind controller to lower the shades. It's telling the HVAC system to lower the fan noise for better audio. It's an orchestrator.
And what about the room scheduler panel, the little screen outside the door?
That's the traffic cop of the meeting space. Its primary job is deep calendar integration. It has to pull data in real time from the organization's backend, whether that's Microsoft Exchange, Google Workspace, or Office 365. That's how it shows the red busy or green available status.
But the logic goes both ways, right?
It has to. If I walk up to an empty room and book it for 30 minutes directly on the panel, it has to immediately write that information back to the central server so that nobody else can book it from their Outlook calendar. It has to prevent that classic double booking conflict. Some advanced ones even have occupancy sensors, so if you book a room and don't show up within 10 minutes, it automatically releases the room back into the pool.
That's really smart. It's about optimizing the real estate.
It's all about making the technology serve the workflow, not the other way around.
Okay, so we've collected all our signals. We have video, we have audio, and we have user commands.
Yeah.
Now we move to the belly of the beast. Section 2, the processing layer, the brain of the entire system.
This is absolutely where the heavy lifting happens. All those clean signals we gathered now need to be routed, mixed, and manipulated. Let's start with video processing.
The central hub for that is the video switcher or matrix switcher.
Right. At its simplest, a switcher lets you choose which source to send at the display. But in enterprise AV, a switcher is almost always also a scaler.
Scaling. Why is that so critical?
Because in a real-world meeting, you have no control over what people bring in. You might have one person's laptop sending a 1080p signal, a 4K camera feed, and maybe a legacy PC sending some weird non-standard resolution. If you send those raw signals directly to a high-resolution display, the display will constantly be trying to adjust. It will flicker or go black or just show a no-signal error.
So the scaler fixes that.
The scaler is the universal translator. It mathematically resizes every single incoming image so that they all perfectly match the native resolution of the output display. It creates one common format so the display is always receiving a stable, clean signal it understands.
Now, what if your display isn't just one screen? What about massive video walls, like in a lobby or a network operations center? You need something more powerful.
You do. You need a specialized video wall processor. Its job is incredibly complex. If you're building a video wall out of, say, 4 screens and a 2x2 grid, you have to account for the bezels, the physical plastic or metal frames of the individual displays.
If you just split the image into 4 quadrants, the lines won't match up.
A diagonal line would look jagged and broken. A person's face would be distorted. The processor performs what's called bezel correction. It digitally hides the pixels that would fall behind the physical frames. So to your eye, the image looks perfectly continuous, as if you're looking through a single window pane.
It's creating an illusion.
A very precise mathematical illusion. These processors also handle complex windowing, allowing you to show multiple sources on the wall at once, and color calibration, ensuring all the screens match each other perfectly.
Okay, I want to talk about something that you mentioned is the cause of, I think you said 90% of no signal issues, the digital handshake,
Mm.
EDID and HDCP.
They are the bane of many technicians' existence, but they're essential. Let's start with EDID. It stands for Extended Display Identification Data. The simplest way to think of it is as a digital business card.
A business card for the display.
Exactly. When you plug your laptop in, the display system sends its card to your laptop. It says, "Hi, I'm a 4K projector. I support these resolutions and these refresh rates." Your laptop's graphics card reads that information and automatically sends the best possible signal.
So what's the problem?
The problem is complexity. The signal doesn't go directly from the laptop to the screen. It goes through a switcher, a scaler, maybe a distribution amplifier. If any one of those devices corrupts that EDID data, the laptop gets confused. It might send a signal the screen can't handle or no signal at all. A huge part of the system integrator's job is managing that EDID handshake. Sometimes we even have to spoof it. Tell the laptop it's connected to a simple, generic monitor so it doesn't get confused by all the complex gear in the middle.
And what about the other half of that handshake, HDCP?
HDCP is the bouncer at the club. It stands for High Bandwidth Digital Content Protection. It's the anti-piracy protocol built into HDMI. If you try to play a protected movie from Netflix or a Blu-ray on your laptop, the laptop does a security check. It asks every single device in the chain, the cable, the switcher, the display, are you a secure, trusted device?
And if none of them isn't?
If your fancy video switcher isn't HDCP compliant, or if the key exchange fails for any reason, the laptop simply cuts the video feed. You just get a black screen or a snow pattern. Managing these encryption keys as they pass through the system is a huge, huge part of making a system reliable.
Okay, let's pivot from video processing to audio processing.
Ah.
We mentioned it briefly before, but let's do a deep dive on the DSP, the digital signal processor.
If the video switcher is the traffic cop, the DSP is, I guess it's the sound engineer in a box.
Yeah.
It takes all the raw audio from the microphones and cleans it, refines it, and makes it intelligible. And the single biggest function it performs is AEC.
Acoustic echo cancellation. We need to explain this one really clearly because echo is the absolute enemy of remote communication.
It truly is. Okay, let's set up the scenario. I'm in a conference room with you, and we're on a video call with a colleague in Tokyo. When our colleague in Tokyo speaks, her voice comes out of the loudspeakers here in our room. Now, our microphones in the room, the same ones that are supposed to be picking up our voices, also hear her voice coming out of our speakers.
Right. It's just sound in the room.
It's just sound in the room.
Yeah.
If we send that sound back down the line to Tokyo, our colleague will hear her own voice being played back to her, but on a delay. That is echo, and it makes conversation impossible.
So how does the DSP stop it from happening?
In a word, subtraction. It's incredibly clever. The DSP knows exactly what audio signal it just sent to the loudspeakers. It keeps a copy of that signal, which we call a reference signal.
Okay.
It then listens very carefully to the microphone input. It's looking for the waveform of that reference signal. When it finds it, it performs a real-time mathematical subtraction. It literally removes the sound of the loudspeaker from the microphone signal, leaving only the sound of our voices to be sent to Tokyo.
And it has to do this continuously with zero audible artifacts. That is an incredible amount of processing power.
It happens in milliseconds. A good DSP can achieve over 40 decibels of echo reduction, which is phenomenal. And it's doing more than just AEC, it's also performing noise reduction. It identifies the constant, steady hum of an HVAC system or projector fan and filters that out.
And it also helps with people who talk too loudly or too quietly.
Right. That's AGC, or automatic gain control. It's like having a sound engineer writing the faders. It gently boosts the volume of the quiet, mumbling talker and gently reduces the volume of the loud talker so that everyone sounds at a consistent, comfortable level to the people on the far end.
Now, here's a point of confusion for a lot of people making buying decisions. We have the DSP, which is this powerful audio brain. But we also hear about codecs and all-in-one VC bars. How do all these pieces relate to each other?
This is the classic all-in-one versus separates debate. It's like, Home audio. Do you buy a soundbar or do you buy a separate receiver and speakers? So a codec, that's short for coder decoder, is the computer that actually runs the meeting software like Zoom or Microsoft Teams. It handles the call connection, the video compression, all the network protocols.
Okay, so that's the core of the meeting.
Right. Now, a VC bar or a video bar combines the camera, the microphones, the speakers, and the codec all into one single plastic bar that you mount above or below a display.
Which sounds very convenient.
It's fantastic for huddle rooms and small meeting rooms. It's quick to install, it's cost effective. But physics has its limits. In a VC bar, the microphone is physically right next to the speaker. The AEC has to work incredibly hard.
So in a large room.
In a large room, a VC bar fails spectacularly. The built-in speakers just aren't powerful enough to fill the space, and the microphones are too far away from the people at the back of the table to pick them up clearly.
And that's where you need the dedicated DSP.
That's exactly where you need a component system. You use the codec just to run the call, but you offload all of the audio heavy lifting to a dedicated, separate DSP, which is then connected to powerful ceiling mics and professionally installed wall speakers. The rule of thumb is really simple. Small, simple room. A VC bar is a great choice. Large, complex, or important room. You need a codec plus a dedicated DSP, no question.
Got it. And the final piece of this processing layer, the thing that orchestrates everything we've talked about, is the control system processor.
This is the brain that handles pure logic. It's all about if-then statements. If the user presses this button, then do these 10 things in this specific order.
And it's a bridge between different types of hardware and software.
It's the ultimate translator. In a single automation queue, it might need to speak IT to the network switcher, RS-232 serial to an older projector, infrared to a TV, and trigger physical relays to make a projection screen motor come down. A programmer writes actual code, a script, to define that logic. When the user presses the Start Meeting button, turn on the projector, wait 5 seconds for it to warm up, then drop the screen, then set the audio level to 70%.
It turns a complex 10-step process into a single reliable button press.
That's the entire goal of good control programming, to hide the complexity from the end user.
We have collected and processed the signal. It's been cleaned, scaled, and routed. Now it has to go somewhere for a human to see or hear it. Section 3, the output layer. The destination.
Let's start with the visual outputs. We have the classic professional LCD displays, but the high-end standard, especially for large, seamless images, is rapidly shifting to active LED or direct view LED.
Right, the technology you see in Times Square, but for the boardroom. I hear about pixel pitch a lot when people discuss these. P1.2, PD.5, what does that math actually mean for the viewer?
Pixel pitch is the physical distance, in millimeters, from the center of one tiny LED cluster to the center of the next one. So a P2.5 wall has 2.5 millimeters of spacing between its pixels. From a distance, your eye blends the light together into a solid image. But if you stand too close, you start to see the black gaps between the pixels. It's called the screen door effect.
So smaller number is better.
A smaller number means the pixels are tighter together, which means you can stand closer before the image breaks down. For a corporate boardroom, where people might be sitting just 10 feet away, you need a very fine pitch, like a P1.2 or even a P0.9. The pixels are so incredibly tight that it looks like liquid video, even up close.
But they are significantly more expensive.
Very, but they offer things no other technology can. They are completely seamless. You build them out of smaller modular cabinets to create a wall 30 feet wide with absolutely no black lines or bezels. And unlike projectors, they are bright enough to look stunning even with all the lights on and the window blinds open.
Speaking of projectors, with this LED technology getting so good, are projectors becoming obsolete?
Not yet. For very large venues like auditoriums or lecture halls, projectors still offer the best price per inch. And the technology has moved to laser projectors now, which means no more expensive lamps to change every few months. The light source lasts for 20,000 hours.
And for ultra-widescreen applications?
That's where we use a technique called edge blending. We take 2 or even 3 projectors and we slightly overlap their images. The video processor then digitally and invisibly fades the edges where they overlap, so it looks like one single, massive, seamless, widescreen image. It's very effective.
Let's move to a different kind of output. Recording and streaming. This is absolutely vital now for company town halls or university lectures.
The key piece of hardware here is the dedicated hardware encoder. A lot of people try to stream important events using a PC and free software like OBS. But a PC is a general-purpose device. It can crash. Windows decides to do an update in the middle of your CEO's speech.
That would be a bad day.
A career-limiting day. A hardware encoder is a dedicated appliance. It's a small box that takes in an HDMI signal. It uses a dedicated chip to compress it into a standard format like H.264, and it pushes that stream reliably to the network. It does one thing, and it doesn't crash.
And it sends that stream to a CDN, right? A content delivery network.
That's right. You don't stream directly from the appliance to thousands of viewers. You send one high-quality stream from your encoder to a service like Akamai or YouTube or Microsoft Stream. The entire workflow is capture in the room, encode on the appliance, package in the cloud, and deliver via the CDN. The CDN handles the immense task of distributing that stream to 10,000 employees simultaneously without your internal corporate network grinding to a halt.
Okay, we have all the individual components now. We understand inputs, processing, and outputs. Let's put them all together. Section 4. Real-world system architectures. Let's build a few common rooms, mentally. First up, the smart classroom.
Okay, the mission here is hybrid learning. You need to serve the students in the room and the students watching remotely, both live and on demand.
So what are the inputs?
For inputs, you have a teacher tracking camera mounted at the back of the room that automatically follows the professor as they move. You'd have ceiling mics to capture student questions clearly. And of course, the professor's laptop for their slides.
And the processing.
The heart would be a presentation switcher. It would take the camera feed and the professor's laptop feed and combine them into a side-by-side or picture-in-picture view. For outputs, that combined feed goes to the main projector for the students in the class. And critically, it also goes to a lecture capture appliance.
What does that appliance do?
That box records the entire session as a video file and is programmed to automatically upload it to the university's LMS, their learning management system, like Canvas or Blackboard, as soon as the class is over.
So the automation saves the professor from ever having to be a video editor.
Exactly. The technology does the work. Okay, scenario B. The hybrid boardroom. This is the premium experience. No expense spared.
This is the big budget flagship room.
For visuals.
Yeah.
Dual 98-inch 4K displays side by side. One for content, one for the remote participants. But at the table, you'd have retractable monitors. These are motorized screens that elegantly rise up out of the table for each seating position.
Why do you need those if you have the giant screens on the wall?
It solves the problem of trying to read fine print, like on a spreadsheet, from 20 feet away. It gives everyone a personal, close-up view. For audio, you'd have the beamforming ceiling mics, obviously. But the speakers would be something special. We would use beam steering speakers.
Beam steering speakers. I've heard of beam steering mics, but not speakers.
It's the exact same principle, but in reverse. These are tall, thin column speakers with multiple drivers. Using a DSP, you can digitally steer the sound energy down towards the seated audience and away from reflective surfaces like the glass walls and the ceiling.
So you get less echo and reverberation.
You get incredibly clear, direct sound, even in a room with terrible acoustics. It makes the audio sound much more intimate and intelligible.
Okay, fantastic. And finally, a very different setup. Scenario C, the digital signage network.
Right, this is a completely distributed system, not a single room. The architecture starts with the cloud-based CMS, a content management system. This is where the marketing or corporate comms team uploads videos, graphics, and schedules.
And that content gets pushed out from the cloud.
Exactly. That content is pushed over the internet to dozens or hundreds of small media players. These are little computers hidden behind the screens in the lobby, the cafeteria, the elevators. They download the content and play it back based on the schedule.
What's the critical piece that makes this an architecture, and not just a bunch of TVs with USB sticks?
Life safety integration. This is non-negotiable in a professional system. The signage network is tied directly into the building's fire alarm system. If that alarm ever trips, the CMS gets a trigger signal. It immediately overrides all scheduled content, and every single screen in the building stops playing the cafeteria menu and flashes a bright red evacuation map with arrows pointing to the nearest exit.
That's a level of integration and intelligence you just don't get with a consumer-grade solution.
That is the definition of architecture. It's a system working for the enterprise, not just a display.
This brings us perfectly to the underlying foundation for almost everything we've discussed. Section 5, the network architecture. AD used to be its own world of weird, separate cables. Now it lives on the IT network, and I know from experience IT managers get very nervous about that.
As they should. Pro AV traffic is a bandwidth hog. A single stream of uncompressed 4K video is massive. And audio traffic, while not as heavy, is extremely sensitive to latency and jitter. If you just dump all that AV gear onto the same flat network as the accounting department's PCs and the guest Wi-Fi,
You're going to have a bad time.
you're going to have a very bad time. The moment someone starts downloading a huge file, your audio might glitch or your video might freeze. We solve this with segmentation specifically by using VLANs, which stands for Virtual Local Area Networks.
And this is the highway lane analogy you mentioned earlier.
It's the perfect analogy. We take a single physical network switch, a single cable, and we use software to logically carve it up into separate parallel lanes. So VLAN 10 might be for controlled traffic, tiny, fast command packets. VLAN 20 is reserved for audio, specifically Dante, which needs perfect clock synchronization. VLAN 30 is the big wide lane for heavy video traffic like AV over IP. And VLAN 40 is for all the regular corporate data.
And the traffic in one lane can't interfere with the traffic in another.
Never. The video traffic in its lane will never, ever touch the accounting data in its lane. It ensures performance and also provides a layer of security.
And what about QoS? I hear that term a lot. Quality of service.
QoS is the VIP pass for the highway. It's a set of rules you program into the network switches. It tells them, in case of a traffic jam or congestion, always let the packets in the audio VLAN and the video VLAN go through first. You're prioritizing real-time communication over things that can wait, like an email download.
And another network technology that has changed installation dramatically is CoE power over Ethernet.
A massive labor and cost saver. We can now power dozens of devices, cameras, touch panels, clocks, scheduling panels, and even some small speakers directly from the network switch itself through the same single Ethernet cable that carries the data.
So no need for an electrician to run a 110-volt power outlet to every single one of those locations.
Exactly. It simplifies cabling dramatically and makes installations much faster and cleaner.
Okay, Section 6. The software ecosystem. The hardware is all connected by the network, but it's software that brings it to life. We've touched on control programming, but what about the management and analytics side?
This is the new frontier, and it's all about cloud monitoring and management. Platforms from major manufacturers allow an IT department to see the health and status of every single AV device across their entire global enterprise from a single web browser.
So it's proactive, not reactive.
That's the goal. The software can send you an alert that says, the projector lamp in room 304 on the third floor of the London office has 10% of its life left, or the codec in the main boardroom in New York has gone offline. It allows the IT team to identify and often fix problems before the user even walks into the room and discovers them.
And it provides data, Ro.
A ton of data. You can see which rooms are used most often, what sources people use the most, when devices are powered on and off. This data is invaluable for making future technology investment decisions and for optimizing real estate usage.
Let's talk about making this all a reality. Section 7. Project execution. It's one thing to look at a nice diagram, but it's another thing entirely to build it on a messy, active construction site.
It's a highly disciplined, multi-phase process. It's not just plugging things in. Phase 1 is design. This is where the system integrator creates detailed CAD drawings, signal flow schematics, audio coverage heat maps, and power and thermal calculations. You've got to solve all the physics problems on paper first.
Then the physical work starts.
Right. Phase 2 is installation. This is the hard labor. Pulling miles of cable through conduit, mounting heavy displays and speakers, building and wiring the equipment racks. It has to be done meticulously.
And once it's wired, it needs its brain.
That's phase 3, programming. The control system programmer writes the logic code. The DSP programmer configures the audio processing. The network engineer configures the switches. This is where the system's intelligence is born. Then comes phase 4, testing or commissioning.
Verifying every single connection.
Every signal path, every button press, every automation cue, you have to test for every possible contingency. And finally, the most important and often most overlooked phase, phase 5, training and handover.
Because if the users don't know how to use it,
then the entire multi-million-dollar investment is worthless. You have to teach the users how to press the button, how to connect their devices, and who to call when there's a problem. The handover is the moment the system actually comes to life for the organization.
But even with perfect execution, things do break. Section 8. Troubleshooting and maintenance.
Yeah.
You have a doctor's flowchart methodology for this.
You always follow the signal path. Don't just guess. For a no video issue, the flowchart is, check the source. Is the laptop actually on and outputting video?
Yeah.
Check the cable. Is it plugged in securely at both ends? Check the switcher input light. Check the display input setting, and finally, suspect an EDID handshake issue.
It's a logical process of elimination. What about for audio?
Same logic. For no audio issue, check power, are the amps on? Check game, is the volume turned up on the touch panel? Check for a mute, is a software mute engaged somewhere in the DSP or the conferencing app? Check the amplifier status lights. Check the physical speaker connections.
It's usually the simple things, isn't it? The low-hanging fruit.
90% of video issues are a bad cable or a bad digital handshake. And I would say 90% of audio issues are a mute button being active somewhere in the signal chain that the user isn't aware of.
Finally, let's look ahead. Our last section, Section 9, the future of AV. Where is this grand architecture going in the next 5 to 10 years?
I see three major undeniable trends. The first, as we've touched on, is the dominance of AV over IP. We are moving away from dedicated HDMI and SDI cables almost entirely. In the near future, every device, every camera, microphone, speaker, display will just have a network port. You'll plug it into the nearest wall jack, and software will route the signal. The entire building becomes the matrix switcher.
Okay, that's a huge shift. What's the second trend?
AI and analytics becoming deeply embedded. The room will become sentient in a way. It won't just track who is talking for the camera. It will provide data on meeting sentiment. Are people in the room engaged or bored? It will provide automatic transcription and summaries. It will give facilities and HR real, actionable data on how collaborative spaces are actually being used.
And the third trend?
Cloud management becoming the default. The amount of physical hardware in the room will continue to shrink. The heavy processing for things like video encoding or analytics will move to the cloud or to edge computing servers. The devices in the room will become simpler, more like thin clients.
And you wanted to leave us with a final provocative thought. You called it the death of the room.
I did. It's something to think about. As VR and AR technologies, like what we're seeing with things like the Apple Vision Pro, continue to advance and become mainstream, will we even need physical screens in the same way?
Go on.
If I can put on a comfortable pair of glasses and see a perfect virtual 100-inch screen floating in front of me and see a photorealistic 3D avatar of you sitting across from me, do we really need the expensive mahogany table and the giant LED wall anymore? The grand architecture we spent this whole time discussing might eventually move from the walls of the building and into the frames of our glasses.
That is a wild concept. The ultimate input-output device is the one that's worn directly on your face. The room becomes software.
It's the logical conclusion of the signal flow. The destination is no longer a screen, it's our eyes.
Well, until we are all meeting in the metaverse, I suppose we still have to make sure that HDMI handshake works every time. We have covered the eyes, the ears, the brain, and the nervous system of the modern enterprise. It's crystal clear that AV isn't just about buying gadgets. It's a complex, disciplined engineering architecture.
It truly is. At its heart, it's the bridge between human communication and digital technology.
I really hope this deep dive helps you, our listener, look at your conference room a little differently next time you walk in. Thank you so much for guiding us through this incredible grid.
It was my pleasure.
And thank you all for listening. Keep asking questions and keep diving deep. Goodbye.